All right, everybody. Hey, you guys a video. You guys are going to get a video. All right, so what we're going to do here is we're going to play around with a concept that I thought was really hard to talk about, on the podcast, but brings together a lot of these kind of number theory ideas. So we're going to talk about something called a unit group. Okay, I'm going to write that down. And the unit group is defined by the modulo. I wrote P. It actually doesn't have to be prime, but it's cooler if it is. Sometimes it's cooler if it's not. We're going to go through examples of where it is and where it's not. So first of all, the question arises, what is a unit? Okay. So one of the groups I talk about a lot on the podcast is when n equals 5. That's like one of the smallest prime numbers where we have something that's interesting. So I'm just going to play around now with this. So let's make a group called the unit group. Okay, and then I'm going to tell you guys why it's cool. So we've labeled as a big U and a subscript for the mod 5. Okay. And this group is going to consist of numbers less than 5 that are relatively prime to 5, meaning they have no common factors. Okay, so clearly 1 is such a number. 1 and 5, there's no number to divide both of those. By the way, an example of a number, two numbers that have common factors are, say, 5 and 10. Clearly, 5 and 10 have a common factor of 5. So the thing about when you select P being a prime number, none of the numbers are common factors. So actually 2, 3, and 4 are all relatively prime to the number 5. So this is just a group. We don't know yet that it's a group, by the way. We would prove that it's a group using the 4 axioms, and maybe I'll do that now. So the first cool thing you can do, so like when I'm sitting around doing math, I like to do this exercise where, first of all, we say this is a group under multiplication, so we're going to test that out. Okay, so 1 times 1 is 1, that's in the group. 1 times 2 is 2. That's in the group. 1 times 3 is 3. 1 times 4 equals 4. So far, we're all in the group. 2 times 1 equals 2. 2 times 2 equals 4. 2 times 3 equals, not 6. Almost made a mistake. It is 6 in the integers, but in the group modulo 5, it's 1. And then 2 times 4, by the same reasoning, is 3. Because it's 8 in the integers, and then modulo 5 is 3. Okay, so, and guess what? 2, 4, 1, 3, that's our group. They're all in the, so this is when we're testing the axiom of closure. Okay? Closure means that if you do the operation, the result is in the group. Okay, so let's keep going. 3 times 1 is 3. And notice I already did 1 times 3. Do I really need to do 3 times 1? The answer is yes, because I don't know if this is an abelian group. And remember, we said abelian groups are what's called commutative, which really just means that, and if it is commutative, it just means that the order doesn't matter, meaning 1 times 3 equals 3 times 1. I like to call it the left-rightness because I use the word order later to mean about 7 other things, and it's confusing. So I like to call it left-rightness. So abelian tests the left-rightness. So far, for 1 and 3, they look right. Okay, so 3 times 2 is 6 mod 5, which is 1. And guess what? That's the same as 2 times 3. So maybe this is an abelian group. We may find that out. 3 times 3 is 4. Okay, make sure you guys are clear about that. And 3 times 4 is 2. We did it again. We did it again. We created all the members of the group and every result of multiplications in the group. Okay, let's do 4. 4 times 1 equals 4. 4 times 2 equals 3, which happens to also equal 2 times 4. So maybe, again, it really is starting to look like we have an abelian group. That is cool too. 4 times 3 is 2. And 4 times 4 is 1. Okay. Just this one exercise alone. Let me move myself down so you can see this. You want to really lock your eyes here. There's some very cool things already emerging. First things first, we multiplied every single group. We multiplied every single number by every other number in the group. And guess what? All we got were numbers that are in the group. Okay, so that we've proved closure. Okay, so here's the other thing I kind of want you to notice, because I'm just noticing it, and I think it's very freaking cool. So first things first, if you look at the 4 columns I have, okay, I've got 1, 2, 3, 4, 2, 4, 1, 3, 3, 1, 4, 2, 4, 3, 2, 1. I have basically, by multiplying each number of the group by a different number, I've created 4 different orderings of the group. That may or may not interest you, but that is super interesting to me. Also, if I go across, I look at the rows, I get the same, by the way, I get the same exact pattern. I get the same 4 permutations is what they're called. 1, 2, 3, 4, 2, 4, 1, 3, 3, 1, 4, 2, 4, 3, 2, 1. Super cool. So I can take this unit group and I can multiply all the numbers by one of the numbers and I can reorder them. That is, turns out to be a pretty powerful feature in cryptography, especially if you don't know how many times I've reordered a group, except I'm dealing with the same number in a closed system. Okay. Anything else? So I will say in this group we have an identity element, which is 1. Okay? Meaning every time I multiply a number by 1, I get itself. Right? And then the other thing is, well, okay, is there an inverse element? I would say that so now this goes back now to the question of what is a unit. So a unit is a number that has an inverse, meaning there's a number I can multiply by all 4 of these numbers to get an answer equal to 1, which is my identity. And sometimes we use the letter E to label the identity. Don't ask me why that is, but mathematicians do that. So if you're self-studying in another book and you see E, that's basically the identity element. So what we're looking for are units. And so you can see in every row, there is an answer. You see there is an answer 1. Okay, so for 1 is a very unique number because it's a unit unto itself. It's its own unit, right? So when 1 times 1 equals 1, right? So 1 is a unit with itself. Then I have 2 times 3, and then I have 3 times 2, and I have both of those equal to 1. Okay? So 2 and 3 are units, and sometimes we call them associates as a pair. So 2, 3, like this pair would be associates. But 2 and 3 are units. They happen to be units with each other. 1 is a unit, okay, right? So 1 is a unit, and its 1's associate is 1. 2 is a unit, and it has 2's associate is 3. So let's just remember 2 times 3 equals 1, right? And then we have 4 times 4 is a unit. So 4 times 4 equals 1, right? So 4 is also a unit. And its associate is itself. Its inverse is itself. Okay, so we've actually solved 3. We've proven 3 of the axioms of the group, right? We did closure. We proved the identity. And we proved that an inverse element exists for every element in the group. So the last thing we'll prove is the thing called associativity. So here's where I'm going to use the word order again. This is where we say the order of when we do the operation doesn't matter. So if I take any 3 numbers in the group, let's take 2, 3, and 4, and I take 2, and I want them, so let's take 2, 3, and 4. The question is, does it matter if I multiply 3 and 4 first? Or does it matter if I multiply 2 and 3 first? Now, I think we all know the answer to this. The answer is no, and I could tell you to take my word for it. This associativity is going to work out, but you want to do it. You always want to do it. And it's just part of maybe a little bit of maturity. Even if you know it's going to work, you still kind of do it just to make sure you complete your proof. And to remind yourself that you have a standard of rigor, that you're going to do all the steps and not take any shortcuts. So let's do this one first. The first one is 2 times 12, and that is 224. But mod 5 is 4. All right, cool. Here, if we do 6 first, and by the way, if I really wanted to be on another level of rigor, I wouldn't have done this multiplication. I would have said that 2 times 12 is 2 times 2, and that equals 4. All right? Because there is no such thing as 12 in my system. Okay. So 2 times 3 is 6 times 4, which actually equals 6 is, remember 6 mod 5 is 1. So that's 1 times 4, which equals 4. Right? So, boom. This is axiom number 2. This here, what we did here was proving axiom number 1. We found the identity, really, we'll say in this row. We found the identity. And then we found the inverses here. So it's a group. So that's pretty cool. Now, there's a lot more to do here, and maybe we'll just stop this here and then we'll start it again in another video.